Oh, hi. Welcome back to another lecture on Calculus 1. We are in packet 26 today, and we're going to be talking about the mean value theorem and monotonicity. I feel like this section would be better titled if it explicitly stated the first derivative test right in the name, but they don't. Even though I think that's really one of the two major outcomes. Monotonicity is one of the tools that we use to establish the first derivative test. Yeah. Anyways, I digress. Okay, so we're going to be talking about two things in this section. The first one is going to be the first derivative test, which is going to let us classify points as minimum, maxima, or neither. That statement right there is somewhat misleading. I mean local minima, local maxima, or neither. We spent time last time talking about how to find the absolute minimum maxima. Our second thing that we're going to be talking about is the mean value theorem, and we'll conclude that. I would like to draw your attention to some YouTube videos that I have on this. A couple about the mean value theorem, and one in particular about the first derivative test. So if that style works well for you with those lightboard videos, maybe that would be a good thing to check out. So let's do the first derivative test. I want to make some observations for you. 3 observations. The first thing that I want you to note is that if over an interval, which I'm calling scripty I because I like the way it looks, if over an interval a function has non-negative derivative, that is to say that it's always at least 0, then the function must be increasing on that entire interval. So I've got an interval scripty I, and I know that on this entire thing, f prime is bigger than or equal to 0, which means that on this entire interval, the function is f is increasing over that interval. Likewise, a function with non-positive derivative over an interval, so f prime is never above 0, the function is going to be decreasing over that entire interval. And furthermore, the thing that really gives this power is that the only places that a function can change from increasing to decreasing or decreasing to increasing is at critical points. It's impossible for a function to change from increasing to decreasing or the other way around if there's not a critical point there. The only place it can change is at critical points. That's why they're so critical. What that means is that if we separate the number line into intervals separated by critical points, then we only have to know f prime at a single point in each interval to know its increasing, decreasing behavior. That is to say, if I draw a number line and I call that r, that's the real numbers, I know that here are, say, the critical points. Let's call that C1, C2, C3. Say that these are the only crit points for f. Well, I know, but beyond a shadow of a doubt, that inside of here, f prime has uniform SIGN sign. And it so does on that interval, and that interval, and that interval as well, right? It can only be exactly one of positive or negative, right? F prime is either bigger than 0 or f prime is less than 0 because there's no critical points. And I better throw my little equals on there, even though those will also show up as those places. Okay, so our tactic now is going to be to draw number lines, put critical points on them, and then find out what the increasing or decreasing nature of f is according to the SIGN sign of its first derivative. So let's pair that with another set of realizations, 2 critical realizations. 1, 2. A local maximum is the top of a hill, and when you go over a hill, you first increase and then decrease. And similarly, a local min is a valley. It's a valley. To cross a valley, you have to go down, and then you have to go up, right? Whereas with the max, you went up, and then you went down. You were increasing and then decreasing. You were decreasing and then increasing. So what we're going to do is we're going to pair those with our realizations before. So I'm going to draw myself a curve. Let's call that F. Let's label the local maxima, and I'm going to label those. Here's a max. That's a local maximum. It's not the global maximum because there are other values over here are higher. So this is a local, not global max. Note that it occurs where we have the derivative is 0. So the derivative is, the tangent line is horizontal there. And we were increasing and then decreasing. So if we were to put another copy of the number line down here, right here, f prime is positive, and here f prime is negative. Similarly, take a look at this other point down here. I've got a local minimum, and it is where, if I take a look at my f prime, we're going to be going down, we're decreasing, and then increasing. And that's going to be true for every local minimum. Every local minimum goes decreasing, increasing. Every local maximum goes increasing and then decreasing, because those are hills and valleys, and local mins and local maxes correspond to hills and valleys. It is possible that you have corners and cusps and things like that, and this behavior still works because you still have the critical points separating the intervals over which f is of uniform sign, SIGN sign. So this suggests a test for us, a way for classifying critical points. And so the problem that this solves is essentially analyze the critical points of f, or maybe find all local optima. Those phrasings both would cause us to do the following behavior, this following process, where I really like drawing a number line. That's how I start. I think really in terms of number lines on these. So I'm going to start by drawing a number line, and I'm going to call that R. And I might remind myself that that X happens to live on that number line, to remind myself the space that we're talking about here. And then we're going to find my critical points. Okay, and we'll put those there. And then I need to know the SIGN sign of the derivative on each interval, so that I can use the first derivative test and classify. So critical point 1, critical point 2, critical point 3. I need to know at the critical point, does f prime go from negative to positive? Right? At this critical point, does f go from increasing to decreasing? And how am I going to know that? Well, I know that it is f prime has uniform sign on that interval. And that's true for each of these intervals. Which means that if I choose some test point in between C2 and C3 in this interval, and it doesn't matter which one, this test point could be any point in C2 to C3 as an interval. All I have to do is take and plug that in, and I know that, let's call that T sub 2. All I need to know is what is f prime of t sub 2, namely the sine of that. Right? And so we'll get some signature of the derivative. Say the derivative goes like, the derivative is positive here, it's negative here, it's positive here, and then it's positive out here. Well, all I have to do is look at each one of those things and make the observation, oh, it went from positive to negative. The derivative did. The function went increasing to decreasing. That means I have a max, a local max. Here it went from decreasing to increasing, so I have a local minimum. And here it went from increasing to increasing, and so I don't have either there. And it's just that simple. And I feel like it's really powered by the number line for me. So I prepared a flowchart, and if you don't find flowcharts useful or this flowchart useful, that's fine. But I like having kind of a set of instructions for what to do, and it starts with what we're given. What are we given? We're given 3 things. How do I know? There's a typo right there. How do I know what that I want to engage in this process? I'm given a function. I have an interval, maybe, and I want to find all local optima, not all local optima of f over that interval, which might be optional. So I think the first thing that we need to do is to construct our number line. Draw a line. And then I want you to add your endpoints for the interval I. And it's possible that you might not do this. If we don't have my interval. And that's okay. And then we want to add the critical points to our interval, and this is exactly the same routine as we did for the global optimization process from 4.2. Take the derivative, and then we're going to find where it's either undefined or 0. So we'll take the derivative, and then solve where that derivative is either 0 or undefined. And on both cases, instead of adding them to a table, we're going to mark them on a number line. There is also a table approach to this. I find that the number line works better for me. So now I have my number line as a result of the create number line box. So I've got my line, I drew it, and then I've got my critical points, and then I've got my boundary points. Okay, and so that's what that leads to. So now I need to determine the sign of the derivative. We're going to choose our test points. That's going to be the next thing that we're going to do. So we're going to take our number line with our demarcations. And we're going to choose some test points. Right? And it doesn't matter which value you choose between A and C1. You're just going to choose a point. It doesn't matter which value you choose between C1 and C2. So you might as well choose a nice point. You know, like integers. 0, 1. You know, like sometimes like multiples of pi can be really handy for doing trig stuff. All right, so we're just going to choose our test points. And then we're going to evaluate our derivative. And for each point in the interval here, I'm going to compute f prime of t0. And the only thing I care about is the SIGN sign of it, right? I need to know the SIGN sign of f prime at my test point. Oh, that's supposed to be an F. Right? So for every single one, you're going to label, and you're going to choose as, is it positive or negative, right? Right? You're going to indicate which one of those things it is. And then finally, we're going to classify. We'll ask the question, does the derivative change sign? For each critical point, you're going to ask if the derivative changes sign across it. Is it negative to positive? Right, that's this case. Whoop. The derivative went from negative to positive. F went from decreasing to increasing. Okay, that means you got a local min. Is it positive to negative? Okay, fine. Then you were on a hill and you have a local max. Or is it neither? Was it increasing to increasing? Was it decreasing to decreasing? Both of those things happen. So f prime has the same sign across. Then it doesn't have a local optimum at that critical point. In any case, no matter how that shakes out, we are eventually going to clearly write our conclusion in a way that's digestible by the audience. Let's practice. So let's find all local optima of this cubic polynomial. Okay, cool. I love cubic polynomials, particularly ones that have been specially constructed to be easy to work with, like this one has, like many of our problems in this have. Otherwise, we'll tend to resort to numerical computational tools. So let's go ahead and name it f equals x cubed minus 27x minus 20. And the first thing that I'm going to do is I'm going to draw a number line. I'm not given an interval, fine, so I'm not going to label those things. I'm going to put x right there to indicate that that's the x line. Okay, so I need to add my critical points to it, right? So add endpoints, that didn't happen. Take the derivative of f and then solve where it's undefined and 0. Fine, f prime equals 3x squared minus 27, right? Where is f prime undefined? It's undefined nowhere because it's polynomial. Okay, so then we need to ask, where is f prime equal to 0? Well, that's where 3x squared minus 27 equals 0. Let's divide by 3 everywhere. 0 equals x squared minus 9. 0 equals x plus 3, x minus 3. That means that I have two crit points, 3 and minus 3. 3 and minus 3. So, okay, so I labeled my number line. Now I've got that. Okay, so we got through that step. Fine. So now we're on to determine the sign of the derivative. We're going to choose our test points, and then we're going to evaluate the derivative. So, on this interval right here, that's the interval from minus infinity to minus 3. We need to choose a nice point in here. Oh, let's say 5, because why not? Ooh, I want to do 0 for this one, and let's do, say, 5 for that one. Ooh, that's a minus. Okay. So I need to evaluate the SIGN sign of f prime at each of those places. So I need sign of f prime at minus 5. Fine. F prime at minus 5 is equal to 3 times minus 5 squared minus 27. 3 times 25 minus 27, that's bigger than 0. So I'm going to label this with a big old plus. Okay, f prime at 0 is 3 times 0 squared minus 27, less than 0. So we'll label the big minus. And then f prime at 5 is 3 times 5 squared minus 27. It's bigger than 0. I know that because this is 25, and 3 times 25 is way bigger than 27. So we'll label plus. Okay, so now we labeled with the SIGN sign on each of our intervals. Now we're to classify. Now we're going to look at each of the critical points. We're going to look at every single one of the critical points. And we're going to ask if the derivative changes sign across it. Right? Negative to positive to negative, neither. Positive to negative, increasing to decreasing. That means that we have a max. This one, the function is decreasing and then increasing. That means that we have a min. If you want to be pedantic, we can use the word local right there. All right. So I would now probably start getting close to a conclusion. So f has a local minimum at, let's see here, 3, and a local max at -3. And if you're interested in what those values are, we could ask what's f of 3? That's equal to 27 minus 27 times. I don't think I care about this. Right? If you care about what the actual value is, if you care about what the height of that local minimum and local maximum are, you can plug them into that value. I don't think that's particularly important right now. You can plug in. You know how to evaluate a function, right? This was about classification, and that classification was local min, local max, based on the SIG and sign change in those places, right? Negative to positive, positive to negative for f prime. Let's repeat that. Let's analyze the critical points of this cool function. I love this function. I love things that have like some weird, neat symmetry like this. I think this is a great function. So let's name it. I didn't name it for you. Let's go f equals x squared plus x to the minus 2. Let's draw ourselves a number line. Again, I'm given no interval of restriction. So all I need to do is find the critical points. I do believe that we're going to have some division by 0 critical points here. So let's take f prime 2x minus 2x to the minus 3. That's why I really like writing my things in terms of powers like this, because it makes doing the power rule like really straightforward, and it prevents me going in the wrong direction. Because a common error is to go from -2 to -1, but that's wrong. Okay. So I'm going to ask the question next. Where is f prime undefined? Okay, cool. F prime is going to be undefined. Where? Well, it's going to be undefined where minus 2x to minus 3 is infinity, because I have essentially minus 2 over x cubed, and I have division by 0. And so that's at x equals 0. Fine, 0. The other part of this function, the other summand, this 2x here, can't possibly contribute to that statement. Let's also ask, where is f prime equal to 0? Well, that's fine. We can go 0 equals 2x minus 2x to the minus 3. Let's cancel some 2's, and let's move that over. And I'll get x to the minus 3 equals x. This looks kind of frustrating. And so let's multiply by x cubed on both sides. So then I'll have x to the 0. Put that in red. I wouldn't normally write that. Equals x to the 4th. But x to the 0, that's just 1. So I have x equals positive or negative square root of 1. Actually, it's 4th root of 1. There's some complex roots here. I don't think that square root's really helpful. So I have positive and negative 1. So I'll add those to my number line. Okay. So done with that. Now I need my test points. I'll need 4 test points. Let's make that one be -2 because out here is infinity and it's nice to work with. How about we call that one half, the minus sign? Let's call that one a half and that one 2. I'm just choosing like nice arbitrary, nice values in each interval. All right, so then I need to know the SIGN sign. I need to know the signs at the test points. So I need to know f prime at -2. That's 2 times -2 minus 2 times -2 to the -3. Let's see here. So that's equal to -4 minus 2 times 1/8. And that's got a minus, so that's plus. Okay, that's less than 0. Because that's just a quarter, and -4 plus a quarter is still going to be negative. So we'll label this interval with a big minus. F prime at -1/2. So we're working on our We're working on our next test point. F prime at -1/2 is equal to 2 times -1/2 minus 2 times -1/2. I think I want to put that cube downstairs. This is kind of frustrating for me. So how about I go over a half cubed. -1 minus, ooh, there's a minus sign. Ooh, plus 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 2/8 minus 1. Ooh, plus 16. That's bigger than 0. I don't actually care what the value is. I only care what the SIGN sign is. Of course, if you're doing this on a calculator, this process right here could be sped significantly if you use the trace eval trick or the ants trick. I guess I could have done that right now and saved a significant amount of time in this, but hey, I think it's useful for you to see me do this. So f prime of 1/2 is equal to 2 times 1/2 minus 2/1/2 cubed is 1 minus 16 is less than 0. And then finally, we are so close on this one. F prime of 2 is equal to 2 times 2 minus 2 times 2 to the -3. It's equal to 4 minus 2/8, which is bigger than 0. Okay, right? So for each of my test points, I plugged it in and I found the SIGN sign of my f prime, right? So each of those values is sine of f prime. And now the number line makes the next part basically trivial, where I need to classify, right? And so I've got some critical points. I have -1, 0, and 1. And we'll classify them just by looking at the behavior. First derivative is negative, so it's decreasing, and then it's increasing. We've got a min at -1. We've got a local min. What about at 0? At 0, it goes from positive to negative, so it's max. And then the next one's going to be a min. And I think the number line makes this so easy. Okay. Let's blast through 2 more examples, and then we'll do the mean value theorem and call it a day. So let's analyze the critical points of this cool function. I love it when I see fractional powers, because the fractional powers typically represent something interesting. I would invite you, for all of these examples, to have been plotting them. I guess I could bring up a plot right now, but I'm going to choose to decline. Instead, you could, by all means, pause this and plot this function. Standard window is going to be good for most of these examples. So why don't you unpause and get at your calculator and predict what is going to happen as a result of this. Alrighty. So again, let's name it f equals 1 minus x 2/3. Number line f prime equals 2/3 1 minus x minus 1/3 times minus 1. Where'd that minus 1 come from? Chaining out. Okie dokie. So standard questions. Where is f prime? Undefined. Where is f prime? 0. So I think that our way forward is going to be to rewrite this 1 over 1 minus x to the third. Let's put a minus sign out there. And now we can see, by having dealt with that negative power, that now I've got something down in a denominator, which is what yields, in many cases, these f prime is undefined things. All right, so where is f prime going to be undefined? Well, that's going to be where 1 minus x to the 1/3 equals 0. That's where that happens. So by solving that, well, let's go ahead and cube both sides. Now I have 1 minus x equals 0, so x equals 1. So let's label that. And there's nowhere else. And as far as the question for where is f prime equal to 0, let's see here. So if I write 0 equals minus 2/3 1 over 1 minus x 1/3, I'm going to try to solve for x, right? And so I'm going to multiply by 1 minus x 1/3, explicitly noting that I'm not letting that be 0 right now. Fine. On the left-hand side, 0 equals minus 2/3 times 1. So 0 equals minus 2/3. What an absurd statement. That means that no such critical points exist. So my only critical point is 1. To the left of 1, let's go grab ourselves a test point. 0. To the right, 2. I have 2 intervals. From minus infinity to infinity, split at 1. So let's test f prime at 0 is equal to minus 2/3 times 1 over 1 to the 1/3, which is equal to minus 2/3 is less than 0. So negative, put that in blue, negative. And then finally, let's try it for f prime at 2 is minus 2/3 times 1 over 1 minus 2 to the 1/3 is equal to minus 2/3 times 1 over minus 1 to the 1/3. Those signs cancel and I get something that's bigger than 0. Again, I don't actually care what the value is. I only care what its SIGN sign is, and it's plus. We therefore can determine that we have it's going down, it's going up. So we've got a local, we'll conclude. Didn't leave myself enough space to do this whole thing so I could have like a nice, beautiful conclusion downstairs. But we would say that f has a local min at 1. At x equals 1. I think I want to go back to the previous problem because I think I made a mistake. I think here for this problem, I think my classification is wrong. And the reason is that f, so I'm going to inspect what's going on right here in this previous problem, right? I have x squared plus x is a minus 2. I think that f goes to infinity right here, right? Because like if I put in 0 to this expression right here, I get infinity. So this function, let me draw it in, I don't know, highlighter. This function is going to go like increase off to infinity. Maybe that wasn't the right choice. Boop. I'll do yellow. So it's going to go off to infinity here, and it comes back down from infinity on the other side. And then it goes like that. I think a plot would have helped. There's definitely a strong benefit to plotting these things before you do them. Okay. So yeah, as far as dealing with the point at 0, f isn't defined at here, so this is wrong. So f is not defined at 0, so this is wrong. Sorry. Kind of infinite discontinuity there. Sorry. Okay. I think, so there's this example on finding all local optima of x minus sine x. And I think that this is an interesting, problem. And yeah, let's do it. Okay. So let's call f equals x minus sine of x. Cool. Number line. Great. All right. So this function is continuous. So no f prime undefined crit points. Cool. So now I just need to go f prime equals 1 minus cosine of x. I'll say 0 equals 1 minus cosine of x in order to solve. So that's where cosine of x equals 1. Okay, cool. Cosine of x equals 1. Okay, cosine. Cosine looks like that. So it's 1 here at 0. It's 1 here at 2 pi. It's 1 over here at 4 pi. It's 1 over here at minus 2 pi. Come back up. So interesting behavior on this function is that we have an infinite number of critical points. Okay. So let's mark those. I have 0, 2 pi, 4 pi, 6 pi, minus 2 pi, minus 4 pi. Let's sum it up some test points, okay? Test points. Let's do minus 3 pi, minus pi, pi, 3 pi, 5 pi. Those are my test points. All right, so in order to know the SIGN sign of the derivative, we're gonna plug them in. So I want to know what's f prime of, say, pi. That's equal to 1 minus cosine of pi. What's cosine of pi again? Let's see here. Cosine of pi is all the way on the back of the circle. That's -1, so this is equal to 2. So we found that the derivative is positive. Let's do it for f prime of minus pi. Is minus pi. 1 minus cosine of minus pi. But cosine of minus pi is just -1. This is equal to 2, which is bigger than 0. So we found the first derivative is positive. And that's going to be true for every single one of these intervals, which means that my function looks like something like that. So it's monotonic. It grows. As we go to the right, it never goes back down. So it's got all these critical points. So it's got an infinite number of critical points. But none are local optima. So that's possible. Okay. We have one more thing to cover in this section here, and that's going to be the mean value theorem. The mean value theorem is really cool in the sense that, like, if you drive 60 miles in an hour, it guarantees that at some point you were driving 60 miles an hour. So let's let f be a differentiable function on an open interval from a to b. It's fine if it's differentiable on a closed interval, also fine. We just don't care what happens at the boundary points as far as that goes. And continuous. That means, as far as this goes, the continuous part is f of a and f of b actually exist. I really need those, and there's like no stupid jumps. All right, nice and continuous. Then we are guaranteed, beyond a shadow of a doubt, the existence of a value, at least one, there might be multiples, c in AB, such that f prime of c equals this expression right here. That expression on the right-hand side right there, this thing right here, is the average rate of change over the interval from A to B. I think I want that to be squares. This right here says that this is the derivative. It's the slope of the tangent line. That is to say that somewhere f must take on the average rate of change. I think I need an f prime. F prime must take on the average rate of change. The handwriting is getting sloppy. I'm very hungry. I apologize. We're almost done. Okay, so let's draw a quick diagram. We'll do one of these problems and then be done. We can all go eat a giant bowl of popcorn with MSG and butter on it. Love MSG. Okay, so I've got an interval from A to B. I've got a function, and it doesn't matter what it doesn't matter like what its heights are at the endpoints. We just need it to be nice and differentiable, right? So I've got nice closed things right there. I think I want to try that again. Because I want to exaggerate the difference. So let's make that one go down. Okay, so I'm going to draw the line that connects these points. That line right here, the slope of that line is the average rate of change over AB. And now I want you to take and check this out. So let's draw parallel lines. Oh, look, right here. Look right here. Let's keep doing it. Oh, look, there's another one right here. Oh, and another one right there. Okay? It was guaranteed that at least one of those exists. And the at least is redundant. It's guaranteed that one of those exists. So let's put it into practice. Let's play with the mean value theorem with the square root function over some interval from 4 to 16. Let's demonstrate that it actually holds true. All right, so we need the average rate of change over 416. Fine. So I need f of 4 is equal to 2. F of 16 is equal to 4. So the average rate of change is equal to 4 minus 2 over 16 minus 4. That's f of b minus f of a over b minus a. 2 over 12, 1 over 6. Alrighty. Now, now we're guaranteed that there exists, but it's so much easier just to write it backwards, capital E, a point C such that f prime of C equals a sixth. We're guaranteed to be able to solve it. We might have to use numerical techniques to do it, but we're guaranteed it works. So let's check f prime is equal to 1 over 2 root x. I hope that you're internalizing that root x prime is equal to 1 over 2 root x. And if I go f prime of c is equal to 1 over 2 square root of c, that's equal to 1 over 6, we're guaranteed that we can solve this. We're guaranteed there's a solution. So this is going to be that, let's see here, 1 over root c equals 1 over 3, and multiplied by 2. And then let's reciprocate. C equals, root c equals 3, so c equals 6. Nope, 9. Whew. It is so time for dinner. All right, C is 9 is the place that solves it for me. So as a reminder, what did we just find? Well, f prime of 9 is equal to 1 over 2 times the square root of 9, which is 1 over 6, which is equal to the average rate of change. And we were guaranteed to be able to find a place where that happens. Cool. Okay, that's the mean value theorem. There are other implications of it, which I'm going to pass on this semester. I'll simply say thank you so much for your time today. I really appreciate you, and I'll catch you later.